Oh, cool. Well, thanks for showing up. I'm Randy Levensalor. I'm a principal architect at CableLabs. Some of you guys may know me. I've been around open source for a while. If you're not familiar with CableLabs, we're a nonprofit who focuses on the cable industry. So we don't have products. We do more research, standards, specifications. So if you've used DOCSIS or a cable modem, that's been specified by CableLabs and certified by our subsidiary, and that's kind of where we've worked traditionally. Over the last several years, we're focusing a lot more on network virtualization, wireline convergence, edge compute, which is great for me because we get to bring in all these great open source tools and stacks to run this infrastructure and really make it a lot more agile and dynamic. So today we're going to talk a little bit about cloud gaming at the edge, because I always find it useful to come up with a great use case to show the benefits, and then people can build on it and come up with all these other great use cases. So while we're focusing on the cloud gaming use case, just know a lot of these technologies will apply to other use cases, AR, VR, and maybe even a few things that none of us have thought of today. So gaming, right? What's the hardware today? You have your monitor, one or more displays, you have some input devices, maybe a steering wheel, and your PC with your GPU in it if you're doing the PC gaming, or if you're in the Xbox world, you have your console. And that has to be at home. And if you're like me and play games like once every few years, you go download the new game, and oops, your graphics card doesn't support it. So then you gotta go buy a new CPU. And it just so happened that, over the pandemic, when I wanted to play some games, there was a supply chain shortage. So I came up, with this one project so we could actually host cloud gaming. So it's somewhat selfish because I wanted to play Age of Empires. Anyway, so for cloud gaming, right, we take that server, we put it in the cloud. So, but when you do this, you don't want a worse experience, right? It's not just for the casual gamer like me. We'd also like to see it for more of the intentional gamer, people that are doing this all the time, or even a pro gamer. So we expect, unnoticeable response times. A lot of times that means you're going to try to get things below 15 milliseconds. So that's 15 milliseconds from the time you click the mouse, it goes out to the server, it renders the frame, and it sends the frame back. Right, that's all great. Another benefit is your ping time from your gaming PC to the gaming server. That's definitely going to be better because you're on the same network. It could even be hosted in the same rack. You expect the frame rate to be better. And this is one of the things that was pleasant to me. I have a friend who has a son who's 17 years old, and he lives on his video game. Right? They stayed with us, and he took over my big TV, and come down at 3 in the morning, he's there playing his games. And so one day I took him, and I said, hey, let's play on my system. And he kept looking for my big PC. We're doing one of the open source, one of the free flight simulator programs. And it turns out we actually had a better frame rate than he did on his PC. And it was hosted in the office. And I'm lucky I live close to the office, so the head end for my cable also has a fiber link to our office. So it's about an 8 millisecond ping from my house to the office. And we actually had a better frame rate. And then we took out my phone and connected my Bluetooth keyboard and mouse. Guess what? Still, better frame rate, better resolution than on the PC. And this was enabled through, by offloading it in the cloud. We were actually able to use I guess I shouldn't have probably put my mic on the, the tag. But this way we're actually able to offload. We have a much more powerful GPU. We have 208 volt power, so it's a little more efficient. We have better cooling. So again, the cooling's more efficient than gaming at home. And we get that better experience. But what does that really look like? If you think about the traditional cloud for cloud gaming, is you really have a centralized thing where you have your Wi-Fi network at home, or maybe you're wired if you're paranoid like I am. And then you have your access network. This could be DOCSIS, PON, fixed wireless. It doesn't really matter. You want the same experience no matter where you're connected. And then you go into a head end or central office, and then you go to a metro network, and then some kind of a transit network, and maybe another transit network, and you don't really know what's happening on any of those, even from the service provider perspective. Every once in a while there may be an errant packet that takes a trip across the Atlantic and back, and that'll mess up your latency, and then your frame rate gets messed up, and you have a horrible experience. And then finally you go to the centralized cloud, and even when you're on the cloud, right, what is that networking like? And if you're in a VM, it's really hard to get that guaranteed performance a lot of the times because the hyperscalers are typically oversubscribing the usage. You still have to rent the GPU, and you're paid per gig or per meg of transmitting data, which can quickly exceed the cost of a new PC if you kind of game for 20 hours a week for a couple months. And then finally, you have your gaming residing there. So while this does work, a lot of times you don't know what's happening in that transit network. Sometimes if you're doing like the diffserv bit, so you can actually specify your latency sensitive packet and you don't want to be queued, that gets scrubbed on a lot of these networks. And again, it's just, plus you have physical limitations, right? Every time you hit a switch, every, so many miles you go over even fiber optic cable, you're adding latency. And we don't want latency, right? Latency is our enemy. So let's look at this, this part again. This is where the service provider has control. This part, it's one or more other providers. And again, just the more people you have to bring into it, the more latency, the less predictability you're going to have within your network. So let's look at moving this to the provider network. Again, same experience. You can be running, your hyperscaler software or running Kubernetes. It doesn't really matter, right? We want to support all of those platforms. And then this way we can actually eliminate the cloud and eliminate these transit networks. No matter what, you still have to transit from your system to your gateway to the head end, right? There's no getting around that if you're doing any kind of cloud gaming. So this way we're actually able to remove a lot of that uncertainty. We can allow the subscriber to specify their quality of experience. I want this application on this device to have much lower latency. I want to have this guaranteed bandwidth to do that, and we want the compute to be close. And this is a simple game. I only need 2 gigs of GPU RAM, so that's all you get. Or it's a heavy game, and you want to have 16 gigs. Then you spin up that instance to match what you need for that game. You don't have to build your system based on what you think the specs are going to be over the next 3 years. Right? You can share that system, amortize the cost, all kinds of great benefits. And again, as I mentioned earlier, there's other use cases, right? So this GPU you're using for cloud gaming could be used for running AI ML tasks at other points. So it's really just kind of opening all this up. Plus, you're not necessarily going to have the bottlenecks that you'll have once you leave the access network. So what has to happen? Think about this from the application developer, who's the person who's offering the cloud gaming. Well, first you have to find the location of the edge, right? Well, you're Randy, and well, actually, I have multiple internet connections from my house, so you have to figure out which access network do we want to use, what's the closest path, can we spin up some edge compute there? Some of this, there aren't a lot of APIs today to even support, finding that edge. And then you can use things like ETSI MEC to instantiate your workload on that edge infrastructure. And then you can use some of the 3GPP NaaP APIs to spin up that workload. And then some other APIs to set that quality of experience, but then you're going to need to know what is that underlying network? What node are they on? What frequencies do they have? What channels do they have? And I'm a gaming provider. I don't care, right? You just want to know, can we get that experience? And so we've loaded the application, we've instantiated the application, and then we have to configure network services. Again, this is really hard when you get down to it. You have a shared resource, either shared spectrum or shared fiber, and then you need to monitor it. And a lot of service providers aren't able to expose that data. And a lot of times if you want to tune that slice or that service flow, you have to go in and change, well, this is the bandwidth, which corresponds to frequency, and these channels, and I want this scheduler. And then you may not even be able to get that transparency of what's happening other than data from the application, which doesn't tell you is that latency on the Wi-Fi network or kind of where is that. So that's where we're looking at this project called NaaP. It's Network as a Platform. And we're not necessarily inventing new APIs, so don't take this as Cable's coming up with a new API. I'll talk a little more about the ones we're leveraging. But we really want to set this kind of common NaaP layer between the network and the edge and all the application users. Be a hyperscaler, third-party developers, or even your own internal operations, right? This is hopefully going to be your Swiss Army knife of nice, clean, simple APIs to use to make sure that onboard a service, follow you where you're going. Again, you just kind of go through the list. There's all kinds of great things that we can enable when everything is managed by a single API, as well as being virtual and dynamic. So let's look a little bit about what does the network look like. And again, like I said, when I started, we tried to look a few years out in the future. So this isn't necessarily what the networks look like today, but this is where we're driving. This is wireless-wireline convergence. So we really want to have a single core, this converged core, which those of you who are familiar with 5G know that that looks an awful lot like a 5G core. Well, it turns out the mobile core can support things like devices moving from one network to the other, where fixed networks are fixed and don't support traffic steering, splitting, and switching. So that's kind of why we're looking at the 5G core for the foundation. There's been quite a bit of work that's gone into the core, especially some new features in R16. It's still not 100% complete because we don't have running code that does all of this yet. We're looking at kind of in the midterm, going with the AGF, which is being defined by Broadband Forum for that wireline connectivity. So it's able to support the N1, N2, N3 interfaces between the core and the RAN. And then it is able then to work with the access network. There are a few gaps in that today. We're working on resolving those. And this is similar to kind of your wireless network. You can have your GNOB or your ORAN. Again, the point is we kind of have this single core. We have our own one policy server and then one UDM and AUSF. So we have our unified device and subscriber management system. So whether you're connecting over Wi-Fi to your home network, connecting over 5G roaming in another country, or at the coffee shop, you actually can go back to that core. And if you have subscriptions and things you're paying for, you can actually have that follow with you. If you have different security settings, those will be the same, same firewall, same DDoS protection, no matter the network you're on. All the traffic can be routed through the user plane function, and we can do a lot of the traffic quality experience there off to the data network. Like I said, we have this new thing here, the NaaP API, or we'll call it NEL, the network exposure layer, will expose these functionalities to third parties or internal users. If you want to know more, there's a link, and I've posted the slides so you can click on the link. Published a white paper last week that goes through this and some of the more forward-looking stuff for convergence, where we actually want to get rid of the AGF shim layer and have the wireline networks talk to the core just like the RAN talks to the core. So we really want to kind of get that much tighter integration, though that's several years away from being deployed. So I said I'd talk about what APIs we're using. So again, there's between subscriber interoperability, because maybe I'm playing my game and I'm on a train and I'm going from network to network, and I still want that to work. So we still need that interoperability layer. We are looking at TMF, Broadband Forum, 3GPP. Camara is the one we're really focusing on right now. So CableLabs joined Camara a month ago as a member. We really like a lot of the work they're doing, though it's still very mobile centric. So we're looking at extending that. There is, everything's based on the UEID, and my laptop doesn't really have a SIM card. It's on Wi-Fi, so we need to bring some of this in. Also bring in some of these wireline networks. As we move to that convergence, some of those differences will fall away. And there's still, they've started a lot of work, a lot of great work groups, but some of them you go dig into the code base and there isn't really a lot of code on the structure. And that's where we're actually trying to build this up in our lab, test it out, develop it, work with our members. So our members are the cable operators of the world, as well as a lot of the vendors we work with. Some of these are cable-specific technologies here with profile management, proactive network maintenance, and that's where we can actually go out and identify a fault in the network before the user does. Some of this goes down to deep RF signaling, where there's a standing wave or you got a little water in the line, and we can actually go out and address that before it becomes a problem. And PCMM is just a way to dynamically manage the service flows, which is similar to a network slice on 5G, or your TCON to next gens on GPON, or your LLIDs on EPON. And yes, we've been standing up all of these network types in the lab and understanding the implications and trying to have this, what is the NaaP layer? What can we do that will work across all of these networks? So again, I said we're looking at use cases. Here's another one we've stood up in addition to gaming, which was Speed Boost, where we could use this as the application. And we have an end user application, and you want to play your game. You call into the network exposure layer, and that's able to look up based on your subscriber ID initially. We're working on moving that towards device ID, and identify, oh, Randy, you have PON and 5G fixed wireless. So we're going to create a network slice on the 5G and create a new TCON on your PON network and increase your bandwidth. We're adding things like low latency, so you can use the diff-serve bit if you're familiar with that. That's part of the IP header that can specify your traffic classifier, or L4S, which is more of a higher layer protocol that doesn't get scrubbed by a lot of the transit providers. And you can say, hey, with this device, if it has that bit set, or it's going to this destination, or it's this flow, give it extra bandwidth. We've done this. We've run it in the lab with our own NaaP API that supports it. For DOCSIS, we're actually using ONAP and Open Daylight to call the PCMM. For the PON and the 5G, we're just talking to those cores directly. So, yeah. And then, all right. I talked really fast. Oh, no, we're 20 minutes in. Okay, that's about where I wanted to be. So for some of the ongoing activity, right, we're still looking at capturing more use cases. A lot of these are being driven by our members, as well as some vendors we're working with. We're really trying to align the convergence strategy, architecture, and development. So kind of looking at, what does that network look like? What elements do we need? As well as actually running it, right? Because we're all open source, and we all want to see running code before we believe anything works. We are going to publish this catalog. We're leveraging a lot of other projects. We're not trying to create a new API. Kind of the new part that we're providing is this single catalog that points into, are you using a 3GPP API? Are you using Camara? And looking at both, largely the northbound APIs, but also some of the southbound APIs of NaaP. So how can you control this? So, for instance, with, managing the user device, we want to use TR369 from MEF, but for some of the bandwidth stuff, we may be using BBF APIs, and of course, a lot of 3GPP in there. We're, gap analysis. Again, as you're writing it, it's really easy to do the gap analysis for seeing, oh, this doesn't work. Like, how are we going to track the subscriber ID, the user ID for a laptop that doesn't have a SIM card? Again, kind of keep refining this API catalog. Again, we're open to work with folks. We're in Camara, we're in 3GPP, we're in lots of other standards bodies as well, trying to drive this. And we're hosting this. We have our 10G lab that we call, if you've seen the marketing, right? Cable doesn't have 5G, we have 10G. Don't ask me, I'm not marketing. But we actually are hosting and bringing in more vendors. So if you are a vendor and want to participate in any of these proofs of concepts or have other use cases, please reach out. We are really open to it. We have a few vendors that just give them VPN access and let them bring it up, as well as members who work in the lab. So I wanted to leave 10 minutes for Q&A, and we got a little less than 10 minutes. So go ahead. Sure.
Thanks, very interesting. So, I understand we have a lot of gaps to get quite to what we can work with frame rates and speed and all that. But I see a tension here, right? On the one hand, we want to integrate, the challenge is connected. Right? So you have a game server, say, going back to the original use case, right? The game server, and you want to connect it to the existing network there. But the tension is always with between connectivity and isolation. Right? I would call this a radical multi-tenant. Right? So
Yes.
In the usual cloud scenario, if you have a data center, you can do physical separation sometimes. If it's physically programming switch, it's Microsoft running its service.
Yes.
But it gets much messier in the edge, right? Because you're much more constrained and much more shared. So I wonder, from your perspective, working very closely with some of these APIs, where do you see us really thinking about isolation very carefully, and how do we do that? Thinking of network slicing and 5G and everything. There are so many narratives, but how do we bring this together?
Right, yeah, and that's a great point, and that's something we do look at, and also where is the edge, right? Is it on the customer premises? Is it hanging from a pole, or is it kind of in a head end or a regional data center? And some of that's going to depend on where you're located, right? In some places, the edge may actually be a hyperscale cloud, right? Probably here, I bet there's some great connectivity to some clouds. But the isolation, yeah, one of the strategies we're looking at is what we call a dual stack approach. So the core network infrastructure is run on one instance of Kubernetes, or three separate Kubernetes clusters, because you need HA, and then all the user plane workloads are going to be run on a separate infrastructure. So that way you're not actually running the core infrastructure with the applications on the exact same nodes. That way you can get physical isolation as well as network isolation. It does take away some of the great mutual, you're reusing everything, but that's one of the kind of practical things, right? Every once in a while there's this escape from the container exploit that comes out. We've all seen Scepter. So that's part of it. So that is a great point. And the other part is kind of by having these external APIs, we do have that mediation layer where we can actually apply security at the NaaP layer in addition to the security at all the different access points. But yeah, great question. Hope that helps, and happy to talk more about that. Go ahead.
So you mentioned something about if-serve bits and that being scrubbed by the license. Can you elaborate a bit more on that, like what the challenges are there, is there any ways to get around that?
There are some ways where you can make sure that it is set appropriately, and a lot of this cable operators and others are removing that scrubbing as we're starting to use it within our networks. But the other part is you need to control it, because if you start setting every bit, you can have the malicious attack, right? Every bit's set as a high priority bit. So you do need that balance, or and that's where we're looking at letting the customers control that from their site, right? They can do it, but there's a maximum amount of traffic that you can do, because it's a small non-blocking queue. So if you write more to the queue than you can transmit up, then guess what? You're out of luck. So that, and then like I said, yeah, just working with the transit providers to honor that, and some of that is just different contracts. I don't know how far that has progressed, though, just because, again, you're looking at so much data that a lot of times honoring that can mess up your networking, right? You may end up doing queue building on some other traffic that you don't want to do. So that's why kind of having this all within the edge and within a single network, it's much easier to control that end to end. So. Right. Yeah, and that's what we're working on. And the other thing is using L4S, which is the higher level protocol, so it's not being scrubbed. And again, you may have some hops in the network that don't honor that, but at least the portions of the network that are able to honor it will. Yeah. Yeah. Right. Yeah. So basically, for the rendering of the cloud gaming, that would be close, and then where that placement is of the gaming server or the shared gaming server. Yeah, that's one of the things that's it's a little better, because for that latency to you may still have someone who'll have a benefit if it's located closer to them. You could come up with a mediation strategy where you find a location that has equal ping to all participants, but I don't know if there's really a solution out there for that to help kind of get beyond that, right? That's where if you're all in the same service provider, and then that's where some of this, kind of interoperability can also come into play. So you can look at prioritizing that traffic between service providers or between different networks. Yeah, I mean, that's really the best you can do, but at least by being more central, you do have better access. The latency between the head end and that is going to be more predictable than the access network, though we're trying to drive that predictability into the access network as well as into the home with Wi-Fi. Look at Wi-Fi 6 and 6E and 7. There's a lot more ability in there to prioritize that traffic too. So again, you kind of break it up and look at each individual segment. You come up with an approach for that segment, and then hopefully through this single nice API, you're able to manage all of those approaches across all of the segments of the network. No, right now it's mainly done with ping. Or just you look at what is the latency, and a lot of times you have to look at the round trip latency, because especially on the customer premises, you don't have an accurate clock. Sometimes it's only within a second, and latency is far less than that. There are some things you can do to calculate what is the upstream versus the downstream latency, but a lot of that, to really get that accurate, you need to have an accurate clock system like PTP that's powered off of GPS. So for those segments in the network, you can get good visibility for upstream versus downstream latency. But for some of the others, it's we have some methods we're working on how do we better expose that as well. Not just how do we capture it, but how do we expose that. Right. Yep.
You mentioned the fact that you're currently working on an API catalog, and I was wondering if the goal will be to publish the catalog to Camara, or is it already available elsewhere?
Right now, I don't think we've made it publicly accessible yet. It's just for our members and vendors, though our intention is to make it public. And some of that stuff is, is it something that would make sense to put into Camara, or do we host it or find another place to host it, since it's going to cover a variety of APIs from different standards bodies. So that's one of the things that we're working through now. So if there are suggestions, definitely open to that. So it hasn't been decided, other than it will be public. And we don't want to, again, we're trying to limit what would be one-off. So we're trying to push as much things to the other APIs as we can. Or this may end up being, hey, we can just push everything into Camara, and Camara does all the interfaces. So we've only been really deep on Camara for a couple months now. So we're still learning that. Yep.
Curious about your thoughts and observations on HTTP3 and protocols impacting.
So with Quick, there is actually a Quick version that supports L4S, and we've had that tested in the lab with some of the low latency work. So that's one of the nice things with Quicks. Plus, it can reestablish the connection much faster than just doing traditional TCP. So Quicks, obviously, it's meant to reduce latency, so that does help. So we want to try to be as agnostic as we can, but take advantage of those. So we don't, we can't go too deep into the packet, because most packets are going to be encrypted at a certain level, or should be. So, but yeah, with Quicks and Quicks being able to include the L4S bits in it is one of the protocols that does help a lot with doing this. Cool. All right, Frank?
Have you looked at the commercial side of things? Because I think the dream of having client or consumer network signaling is as old as the serve, right? We had that
Yeah.
serve. We never really took off, not because of technical infeasibility, but because of the different dependencies that you either don't have between the different commercial suppliers, right? So you not only have the user and the network, but you have the app supplier and the like. So have you looked into what is different this time so that you believe it's going to go without?
Well, some of it is some of our members have already deployed this, so we are already seeing some of this work out. Some of it is, the ability to have those edge host different application stacks. So, you can have Microsoft, Google, and Amazon all have racks or servers within that point of presence. And so they already have their billing models stood up for that, for that compute, and then there's a separate agreement between kind of the hyperscaler and the service provider for the compute side. And then for the network side, again, that can be part of the subscriber, right? You can have this whole test, right? Does the subscriber sign up to this, or have some way of the subscriber acknowledging that, yes, I do want to either pay extra or use my credits towards this. So there's some of those things are new. Yeah, I said that's kind of really looking at, but there's still challenges, right? Could we have kind of some massive broker that manages and publishes rates, and you can look at, well, you can get 8 milliseconds of latency and pay X, but if you had 2 milliseconds of latency, it's going to be less per compute, or the throughput costs more, because again, there's so many different axes of that cost. But yeah, I think some of that is, it's already being addressed today, and we're already seeing some operators have already deployed this. So yeah. Sure.
This is a question. I was wondering if you compare your solution with what was offered by Google, the Google Stadia. It was a similar concept
Yeah.
where you don't need a powerful PC or laptop, but
Yeah. Well, so we're part of the advantage of this is we aren't looking at what is that platform. So when I did it right for this, we just used Steam on a Windows PC and already had that ecosystem there, and had some extra infrastructure to manage that connection, and used Parsec was the application that has some optimized streaming over like remote desktop. So, or you can have kind of, Microsoft can bring in their Xbox streaming and drop in their Xbox servers there at the edge as well. So we're trying not to focus on kind of this is going to be the winning platform, but how can we support as many platforms as possible within this? And the other point is, right, in certain areas, you're still going to use the cloud, right? I don't want to say that everywhere you're not going to do it, because you may be really close, but there are certain areas in the US where it's 90 millisecond ping from the head end to the nearest cloud. And that's not even counting the access network and the Wi-Fi network. And for those, we have to have edge. And then some places you also have that bandwidth costs and things like that. Well, cool. Well, we're a couple minutes over. I appreciate all the questions. Feel free. I'll be around all week to talk to me now or later. Thank you.